I promised last week that we'd talk much more about counting and make combinatorial proofs much more useful, and that's the plan for today. To start, I want to tie back to the last lecture where we mentioned partitions and their connection with equivalence classes. A partition is a way of splitting up a set into non-overlapping subsets. And we define the partition as a set of sets, and we can call each of the sets within the partition a part. And the partition itself is the set that contains all of the parts. Each of the parts need to contain some elements, and they can't have any elements in common. The intersection between any two parts is empty, but when we union together all of the parts, we get back S. So this means that every element of S belongs to exactly one of the parts in the partition, and all of the parts have at least one element of S. So here we have a partition of the set S. So the partition is a set, and the elements of the partition, the parts, are also sets. And each of these parts is a subset of S, where all of them are non-empty and non-overlapping. And if we were to union them all together, we would get back the original set. Another example comes from the equivalence classes of congruence mod 4 that we talked about at the end of the last lecture. We saw last time that the congruence mod 4 equivalence relation had 4 equivalence classes, and that those equivalence classes were pairwise disjoint and contained all of the integers. And so, if we take the set that contains all 4 of those equivalence classes, that is a partition of the integers. And this connection between equivalence classes and partitions is not a coincidence. In fact, there is a direct correspondence between equivalence classes and partitions. The book proves 2 separate propositions in different sections, but 15.3 says that for every equivalence relation, the equivalence classes form a partition, whereas 16.3 shows how we can construct an equivalence relation from any partition. I'm not going to prove this theorem, but I'll give you a sketch of the components that would be needed, and you can read the details in the textbook. If we have a partition of a set, then we can define a relation on that set where 2 elements are related if they are in the same partition. And we can show that that relation is an equivalence relation by proving that it's reflexive, transitive, and symmetric. And briefly, it's reflexive because each element is in its own part. It's symmetric because if A is in B's part, then B is also in A's part. And it's transitive because if A is in B's part and B is in C's part, then A is in C's part. Given an equivalence relation on some set, the partition is specified by its equivalence classes, so we would need to show that the equivalence classes are all non-empty and pairwise disjoint, and that their union is the original set. Briefly, they're non-empty because we define every equivalence class to correspond to some element. They're disjoint because if we have two elements from different equivalence classes, neither can be in the other's class, otherwise they would be equivalent and we would have only one equivalence class. And since every element belongs to some equivalence class, when we union together all of the equivalence classes, we get the original set. Now let's uphold my promise by making use of equivalence classes and partitions to help with counting. Where equivalence classes come in handy is when we're answering counting questions along the lines of, in how many different ways can we arrange or choose something? And the key idea is that we can start with our previous techniques for counting the total number of arrangements, and those will overcount the number of different options, but then we can use equivalence classes to figure out how much have we overcounted by and adjust for it. An example of this sort of counting different ways question is how many distinct rearrangements are there of a collection of letters where some letters are repeated. If we treat this as a pure list counting problem using the tools that we've seen before, then we could think about how many options are there for the first position of the rearrangement, and here there would be 4 possibilities. But then, depending on what letter we picked for the first position in the list, we would have to branch into different possibilities, because if we picked the M as the first letter, then we would only have 3 options for the next letter, whereas if we picked something else, we would still have 4 options. So a much more convenient way of approaching this counting problem is to first think about what are all of the arrangements if we ignore the fact that the S's are all the same, and then adjust for the number of arrangements of the S that are all equivalent to one another. So here I've artificially made all of the S's distinct from one another and all of the I's distinct from one another and also the P's by giving them different colors. And so now, if we count the number of ways to rearrange this list, that's an easy list counting problem that we already know how to solve. If we're thinking about how to arrange 11 distinct items in a list, we know we have 11 factorial options. And so now the question is, how many of those 11 factorial lists would be equivalent to one another if we took away the coloring of the letters and counted 2 lists that just swap the 2 P's as identical? So on the set of 11 factorial different lists of the letters when they have been colored, we can define an equivalence relation that 2 lists are equivalent if they differ only in the assignment of colors to the same letter. So if we're spelling the same word, that is, we're only changing which P goes where, for example, then we consider those 2 lists equivalent. So with this equivalence relation defined, we can think about the equivalence classes of any given list of letters. So the square brackets here indicate the equivalence class of this list, and we're asking what is the size of that equivalence class. Well, we could get a list that is equivalent to this one by swapping the two p's, or by rearranging the four i's in any possible order, and similarly rearranging the four s's. So we can think about the total number of rearrangements that are equivalent to this one as So for example, since we have 4 different colors of S, there are 4 factorial ways to rearrange those S's while still spelling the same word. And so in total, we have 4 factorial times 4 factorial times 2 factorial ways of rearranging equivalent letters without changing the actual word that we're spelling. And this counting of the number of ways to rearrange the identical letters wasn't specific to this word that we chose. In fact, for any possible list of these same letters, we have 1,152 lists in its equivalence class. And so that means that our original 11 factorial counting of the lists is too large by a factor of 1,152 because every equivalence class contains this many equivalent lists. So what we've done here to figure out the number of different arrangements is to first figure out the size of the set of all arrangements, and then we've defined a partition of that set into equivalence classes, and then by counting the number of elements in each equivalence class, we know that the number of distinct equivalence classes is the number of different arrangements, and so we've divided the total number of arrangements by the size of each equivalence class to get our number of different arrangements. And we can generalize this idea of counting all of the arrangements and then dividing out the repetitions to help us count lots of other quantities. Here I've represented one possible ordering of the players on a basketball team according to their jersey number, and we're asking how many different ways could we select a starting lineup of 5 players from the roster of 15 players. Well, for any given arrangement of the players, we could call the first 5 players in that arrangement the starters. But there are definitely not 15 factorial distinct starting lineups, because if we consider all 15 factorial arrangements, then we have a lot of repeats. In particular, if we were to switch players 2 and 3 here, we would still have the same 5 players in the starting lineup. And likewise, if we were to swap our 2 players from the bench in the ordering, that would still give us the same first 5 and therefore the same starting lineup. So once again, we can try to count how many arrangements are equivalent to this one according to the equivalence relation of gives us the same starting 5. Well, any reordering of the starters would give us the same first 5, and likewise, any rearrangement of the bench players would give us the same starting 5. And so we have 5 starters, and therefore 5 factorial arrangements of the starters, and 10 bench players, and therefore 10 factorial arrangements of the bench players. And so that gives us 5 factorial times 10 factorial rearrangements that don't affect the starting lineup. So again, this reasoning is the same for any starting 5. So we have 5 factorial times 10 factorial as the size of all of the equivalence classes. And so we can take our 15 factorial total orderings and divide by the 5 factorial times 10 factorial size of the equivalence classes to get the number of distinct equivalence classes, which is the number of distinct starting lineups. And we can now generalize this to other sports that have a different number of players on the roster and a different number of players in the starting lineup. So if we have a roster size of n, then the total number of arrangements of all the players would be n factorial. And then if we divide out the rearrangements of just the starters, that would be k factorial arrangements of the starters. And we also want to divide out the number of arrangements of the bench players, and there are n minus k bench players, and so there would be n minus k factorial arrangements of them. And obviously there was nothing special about sports teams here. If we have a set of n options from which we want to choose k of them, then we would have n factorial total arrangements of all the options, and we would divide out the k factorial arrangements of the things we chose and the n minus k arrangements of the things we didn't choose. And this formula is a useful enough one that it has its own name based on the idea of choosing k out of n options. We call this n choose k, and we denote it by n over k in parentheses. And this is always equal to n factorial over k factorial n minus k factorial. This n choose k operator is well defined as long as n and k are natural numbers. It doesn't make sense to have a fractional or negative number of options or choices to make. And we also want n, the size of the set we're choosing from, to be at least as large as k, the number of things that we are choosing. An example we could consider for applying this formula is counting the number of size k subsets of an n-element set. Well, as we've been doing, we could count the number of ways to order all of the elements of the set. And then if we put the first k elements from an ordering into the subset, then we could count how many ways do we end up with equivalent subsets and divide those out. And so if we do as we have been and list all of the elements of this set, then we will have n factorial lists. And for each list, we can consider the first k elements of that list, the elements of the subset. But now we've overcounted, and we need to figure out how many different lists are equivalent in terms of the subset they produce. And we get k factorial arrangements of the elements in the subset and minus k factorial arrangements of the other elements. And so we get n factorial over k factorial and minus k factorial as our number of unique choices of the k elements in the subset. And so again, our answer is n choose k. And I bring up this example both because this will be a sort of thing that we frequently want to count, and to point out that the book actually defines the operation n choose k as the answer to the number of k element subsets of an n element set, and then goes on to eventually work out the formula and all of the other things that this is equivalent to. And so I encourage you to read through the book's version that starts from counting subsets and derives all of the rest from there, and ask me any questions that you have about it. Another name for n choose k is the binomial coefficient, and this name comes from binomial expansion, that is, expanding x plus y to the n. So let's look at some examples of the connection between binomial expansion and n choose k. So our basic binomial has two variables x and y that we are raising to some power. And so when we expand x plus y to the third, we get this as our result of expanding out all of the multiplications. And if we collect up terms, then we have an x cubed, and then we have three different terms that correspond to x squared y. And the reason that there are three of those terms is that we have two x's and a y, and so we're counting the number of ways we can choose one y out of the three variables. And then we have three terms that are x times y squared, and here we are picking two of the variables to be a y. So we get 3 choose 2 times xy squared. And then we have a y cubed term, and here we are picking all three of the variables to be a y. So here we have 3 choose 3 times y cubed, and this 1 times x cubed at the beginning corresponds to choosing 0 of the three variables to be a y. And so the coefficients of this binomial expansion correspond to our power choose the number of y's in that particular term. So in general, if we expand x plus y to the n, then we'll get n choose 0 times x to the n plus n choose 1 times the next term, n choose 2 times the next. And then as we approach the end, we'll have n choose n minus 2 times our x squared y to the n minus 2 term. And so we can represent this more compactly as the sum from k equals 0 up to n of n choose k times the x to the n minus k y to the k term of this sum. And so n choose k gives us the coefficient for the kth term indexing from 0 of the expansion of x plus y to the n. Once again, the book proves this in greater detail, and it also proves the connection between these binomial coefficients and Pascal's triangle. Pascal's triangle starts with a 1 at the top and along each of the edges, and then all of the interior terms are the sum of the terms above and to the left plus above and to the right. And you may have seen before the connection between a row of Pascal's triangle and the coefficients of a binomial expansion. And so we can find the value of n choose k in the nth row and kth position of Pascal's triangle if we index the rows and positions starting from 0. Over the remainder of the semester, we will have several more opportunities to count the number of subsets or other things that we can choose, and so we will make frequent use of n choose k and the related methods and formulas.